Finally, I'd like to just do one video devoted just to examples. So to start with, we're given a differential equation dy dx equals 2 times the quantity y minus 1, and we're asked which of the following is a solution. So what I often see in a situation like this is students will overcomplicate a problem to try to find a solution and then take their solution and check it against the ones given. But remember that it's always easier to take a given function and check that it's a solution than to come up with the solution from scratch. So we don't even have to try to come up with one. We're given actually 4 possibilities here. So the way that I check this is we want to see that when I take the derivative of the given function, is it equal to 2 times that function minus 1? So to start with here, right, we can think of, in this first example, dy dx would be negative 2e to the 2x. And 2 times the quantity y minus 1 would be 2 times negative e to the 2x, which would be negative 2 e to the 2x. These are equal. So we would say that, yes, this function is a potential solution to what we have above. For the second one, if I take the derivative of this function, I get 2e to the 2x. And if I take 2 times this function minus 1, I get 2e to the 2x. Again, I end up with something that's the same on both sides. So this is also a solution to this differential equation. For this third function, the derivative would be 2e to the 2x. Oops. There we go. Minus 2. And if I were to take 2 times the quantity y minus 1, this would give me 2 times e to the 2x minus 2x minus 1. These are not equal for all values of x. So I'm going to say that this one is not a solution. And then finally, this last one, the derivative would be 2e to the 2x. And in finding 2 times the quantity y minus 1, we would get 2 times 1 plus e to the 2x, which is 2 plus 2e to the 2x. And that's not quite the same as what we got over here. So again, this one is likewise not a solution. So here, we're not given any potential solutions, so the approach will be different. I guess in question 1, we're not given any solutions. So here we're asked for the equilibrium solutions. And recall that that is much easier than coming up with the general solution. And to find those, we set 0 equal to dy dt, which means we're setting 0 equal to 1/2 y squared minus 1. Which means we want to know when is y squared minus 1 equal to 0. That happens when y squared is 1. So we end up with 2 possibilities, y equals minus 1 and y equals positive 1. Those are going to be our equilibrium solutions. Box those. In the second part of this question, we are, much like the first example, given a function, and essentially we're told that that is a solution, but we need to verify that. So that means that we need to take the derivative of this function, and then we need to compare it to 1/2 this function squared minus 1. So to start with, the derivative here, if I use the quotient rule, the derivative of the top is c e to the t. We multiply that by the bottom, and we can then take the minus the derivative of the bottom times the top. In the denominator, we square the given denominator. So, of course, this looks complex. However, we can work through this and try to see what we have. The numerator is going to involve, let's see, c e to the t minus c e to the t squared. And we're going to have plus c e to the t plus c e to the t squared over this denominator. So what we're able to do is cancel the c e to the t squared. And what we're now left with is I have, let me go back to the blue. I have now 2 c e to the t in the numerator, and then 1 minus c, I lost my squared here, c e to the t squared in the denominator. So looking at that, what I now want to look at is what happens when I take the square of this function and subtract 1 and multiply that by 1/2. So what we'll be able to say here, first of all, is, so I'm working on the right hand side, y squared minus 1 is 1 plus c e to the t over 1 minus c e to the t, all squared, minus 1. Now, if I square this, I'm going to get, let's see, let me leave, let's see, I'm going to leave this, I'm going to leave the denominator as this squared, only because I have that same denominator over here, and my task is to try to equate these. But in the top, I'll multiply this out, that this would be 1 plus 2c e to the t plus the square, so c squared e to the 2t. So that's me writing out the squared term, minus 1. But notice that one way to write 1, if I want to get a common denominator here, is to write it as this. So now I have the common denominator of ce to the t, all squared. And I have 1 plus 2c e to the t plus c squared e to the 2t minus the, let me fix my actual common denominator. This should be a 1 minus in there. So this should be a 1 minus here and a 1 minus here. So this should also be a 1 minus. Okay, so now this is correct. And squaring out that 1 minus c e to the t, I'm going to keep that in parentheses. And so we're going to have a 1. I'm going to have a minus 2c e to the t. And I'm going to have a plus c squared e to the 2t. However, looking at what's positive and what's negative, we have a positive 1 and we're subtracting 1. And we have a positive c squared e to the 2t and we're subtracting one of those. That leaves us with just these terms, which are both positive. And putting them all together, that's going to give me 4 of those. So I have here in the numerator 4 c e to the t, and in the denominator 1 minus c e to the t quantity squared. But importantly, if we go back to the differential equation, I'm missing so far the multiplier of 1/2. So really the right hand side would be 1/2 y squared minus 1, which now we know is 1/2 what I ended up with in the previous line. And that makes this now, instead of 4, a 2 in the numerator. Importantly, if you look back at our dy dt, that's exactly what we found that equals. So we've just shown for the proposed function, it does satisfy the differential equation. So this is the way that we've shown that this is a solution. And we see here that, again, this is just the general solution. If we'd been given an initial condition, then we would be able to specify a particular value of C that would make this a solution. And then finally, one last example that's a little bit different, and we'll see, we're going to actually have a whole set of lectures kind of devoted to what we call these kind of word problems related to differential equations. And so we're looking at blood concentration here. And there's a few key things that are going to allow us to set this up. One thing I want to point out in this problem, so we're told the concentration of a drug in a patient's bloodstream declines at a rate proportional to the concentration. After the injection, the concentration is 12, and 2 hours later, it is 6.5. So we want to find a formula for y of t, which is we're going to use to represent the concentration of this drug t hours after injection. So notice that the information we're given about y is actually its derivative, because we're saying it's declining at a rate. So bringing in the word rate means that we are describing really y prime of t. The other thing I really want to emphasize here is it says that it declines at a rate proportional to. So just for reference, because this comes up in these types of applications, y is proportional to x if y is a constant times x. So when we read proportional to, think constant multiple. Sometimes you're given that constant. They call this the proportionality constant. So in some applications, you might be provided with a proportionality constant. That just means they're giving you that multiplier that we would use. So looking at this, we want to solve for y of t. And what they're telling us is that dy dt, the rate of change of the concentration, is proportional to, and what is it proportional to? The concentration, but that's exactly what y is. So the rate of change of the concentration is proportional to itself, the concentration. So this is my given setup. We want to solve for y of t. Well, in a previous video, we came up with what I kind of boxed and referred to a fact. Anytime you see a differential equation of this form, dy dt equals a constant times y, then we know that the solution is going to be of the form c e to the k t. So we are allowed to jump right to that because of the form of this differential equation. And of course, now we have these two unknown constants, but I haven't used everything in the problem. So when I say given here, we're actually given more than this. We know that right after injection, the value of the function should be 12. Well, we're treating injection as times 0 based off of how this is described. So if I know this, so y of 0 is 12. Well, here's our y function. Let's plug in 0 for t. And so that would give me c e to the k times 0 equals 12. That's just telling me c is 12. So at this point, we can update that our function is 12 e to the kt. But we're not done because we still don't know what k is. But I also have another piece of information. At hours, so at t equals 2, the value should be 6.5. So we can use that. That is, we still have one unknown, but we have another equation we can use. So we used the initial y of 0, and then y of 2 equals 6.5. Again, I go back up to my most updated equation here, and I'm going to plug in 2 for t. That would give me 12e to the 2k. And that should leave us with 6.5. And now we just need to solve for k. So I can divide both sides by 12 to get that e to the 2k equals 6.5 over 12. If I take the natural log of both sides, 2k is the natural log of 6.5 over 12. And then dividing by 2, we get our k value. And so a couple things to think about here. It turns out if you were to put this into a calculator, this is roughly minus 0.3. So we could say that our function is of the form 12e to the minus 0.3t. Now, when you're working through these kinds of applications, it's not a bad idea to think if your answer makes sense. And in particular, what I'm talking here is that I should have expected a negative k value because we would expect the concentration to go down. It says decline, so we would expect that to decrease the longer we move away from the injection. So if I had ended up with a positive k in this problem, I would have known I had made a mistake somewhere. So that's one thing to think of. Related to that, sometimes that might be supplied with the constant. So if this problem had given you a proportionality constant, so suppose they told you that the proportionality constant was 0.3, you would have to be able to deduce that it was negative 0.3 because of the word declines. So that's another thing here. If we are solving for k, that negative is going to come out naturally from our information. But sometimes you might have to take that into consideration if they're trying to supply you with the value of k. Look for some of those keywords to help us decide if that value should actually be negative. In different examples, we'll see things where we expect the quantity to increase with time, and then that's going to be a situation where we'd expect a positive proportionality constant.